So, hello everyone. Welcome to this day three for Rust programming language. I guess we have covered quite a ground in the last 2 days. We covered a lot of things in the Rust. Right, let's see what we covered. So, in the first 2 days, we covered installation. We also looked into Cargo, the package manager. We created a guessing game from the Rust. We also yesterday had quite a bit practice on match clause, uh, and we saw that what expression are in Rust. I guess that's a very essential core concept of Rust to understand the expression and how certain type of Hmm. Expressions are available. If we saw that the loops are also expressions, and that may again evaluate to a certain value, and that can be stored into a variable. Uh, then we also looked into certain data types. We saw that we have primitive data types as well as all the scalar data types as well as compound data types. We looked into integer, different types of integers, floats, boolean, and anything else. Yeah, character, right? And then we also saw compound types. So we have the tuples as well as an arrays. Tuples are can contain any data type, while arrays are grouped uh, by similar data type. Right, we also saw how to access a value inside a tuple, so that can be x dot zero. Zero is we can call it as a coordinate for that particular value inside this tuple, while array are accessed by the index by their usual square brackets along with the index. We also saw that we can also annotate this particular array. So essentially this means it's array of type 32 and it has five values. So we also saw that uh, if we change this size to any other value apart from the number of the elements here, this was throwing us compile time error. We also saw a shorthand notation in case we want to have an array um, that is of size 5. Always remember the second is size 5, and 3, this means that 3 gets repeated by 5, so we have an array of size 5 with all the element as 3. All right, we also saw that by default, again, these arrays are immutable, so if you want to change that, we have to have mute prefixed it with a mute keyword. We also saw functions. We already have seen what macros are, but there are function get called. Again, that's similar to any other programming language. We also saw a return type, and we have a different keyword for a return type. It's arrow operator, kind of arrow operator, like this. And again, we do not need a return because whatever is the last statement, if we do not supply return, it will evaluate to whatever last statement or the expression. Not the or, again, statements and expression are different terms, so whatever is the last expression. So in this case, this will return an error because it's followed by a colon, and this becomes an statement. Control flow, we looked into loops, we looked into if else, we also looked into if else, sorry, else if. So in this case, whatever gets true first gets evaluated and returned, right? And apart from that, if anything else, so for instance, in this example, sx is divisible by 3 is also divisible by 4, or by divisible by 2, but since 3 is 3, this particular clause is first in the list, this gets evaluated and the rest of these do not execute. All right. Again, if is also an expression, so this can also be assigned to a variable, and whatever is the last expression and if that's get evaluated. Again, this will throw an error because these are two different data types, and at compile time, we do not have any way to know which of these will be assigned to this particular variable. Yeah. So repeating code with loop. Loop again, we also saw a special kind of label that you can have with the loops. And essentially why it's required, because your break only works on the inner loop, but if you want to exit or get out of the outer loop, you would use uh, a break statement here. Yeah, again, as I mentioned, loops are expressions, so that value can be evaluated and can be assigned to a variable. Okay, let's check the stream as well. For today, from Rust book. All right, so control flow. We also saw for in. So this can I iterate over the elements in an array that's simplified than a while where we have to have in another variable that would store an index and then iterate over index. So similar to other language, we have another one. So this essentially range over an integer. I also try to range it over say characters. So this seems to work only on integers, I guess, and rev, that will give you a reverse of whatever order we have here. Okay, I guess yesterday we talked about whether we should uh, try this out. I guess first we will go ahead and cover some ground on the Rust, and then I guess we can come back and implement these codes. All right. So ownership. Unique feature and has deep implication for rest of the language. It enables Rust to make memory safe guarantees without needing a garbage collector. So it's important to understand how ownership works. In this chapter, we'll talk about ownership as well as several feature related borrowing slices and how Rust lives. Okay, so it's more about about the memory management in Rust, it seems, and how Rust makes the memory safety guarantees without needing a garbage collector. So it's interesting. So first thing first, what is ownership? Is a set of rules that governs how a REST program manages memory. All have to manage the way they use a computer's memory while running. Okay, all programs have to manage the okay. Some languages have garbage collection that constantly look for. Okay, so some of the languages have the garbage collector, and you have different algorithms for garbage collection, like mark and sweep algorithm, where you are marking whatever memory spaces are not used frequently or out of scope. You just mark them, and in next iteration, you kind of reclaim that memory that is garbage. Okay, so Rust uses a third approach. Memory is managed through a system of ownership with a set of rules that the compiler checks. If any of the rules are violated, the program won't compile. Okay. Okay, so the Rust uses is uses an approach where where you can own a memory based on some rules. So these rules are defined or guaranteed by by the garbage collector. Ownership is a new concept for many programmers. It doesn't take some time to get used to. The good news is that the more experience you become with Rust and the rules of the ownership system, the easier you'll find naturally develop code that is safe and efficient. Okay, so I guess it says that as you code along and you get more experience with Rust, you would have an intuitive understanding of that. Okay, okay. So let's go through stack and heap. Before going to Rust, let's try to think with in terms of other language. So other languages have stack, which hold say local variables or values local to functions. Heap is more common memory area, right, where essentially your memory is shared across different functions or programs. So, system programming language address whether the values on a stack or the affect how the program behaves and why you have to make certain decisions. Okay. Ownership will be discussed in relation to the stack and the heap header. So here is a brief explanation on preparation. Both the stack and heap are parts of memory available to you, your code to use at runtime, but they are structured in different way. All right. The stack store value in order it gets them and removes the value in opposite order. Right. This is why we use a stack. This is last in first out. So you have stack and okay, again it says last in first out. Think of a stack. Okay, I'm not going to do that. Pushing into stack is called popping. That's all stack related functions. Now let's go to heap is less organized. When you put data on the heap, you require a certain amount of space. The memory allocator finds an empty spot in the heap that is big enough, mark it as being in use, and returns a pointer, which is the address. This process is called allocation on the heap, and it is sometimes abbreviated as just allocating. It's simple enough. It's common across other languages as well. All right, so pushing values onto the stack is not considered allocating because the pointer to heap is a known fixed size. You cannot store the pointer on the stack, but when you want to actual data, you must follow the pointer. Think of being seated at a restaurant. When you enter, you state the number of people in your group, and the staff finds an empty table that fits everyone and leads you there. Wow, good analogy here. If someone so says that there is an allocator and to that allocator you are going to ask for the memory and it will go and find in the heap where you can actually actually allocate that piece of memory effectively and it will just return the table number of that particular location. Pushing to the stack is faster than allocating on the heap because allocator never has to search for a place to store new data. All right. Stack is faster. That's good. Accessing data in the heap is slower than accessing data on the stack because, yeah, same thing. If they jump around less in memory, continuing the analogy, consider server at a restaurant taking orders from many table. It's most efficient to get all the orders at one table before moving on to the next table. All right. And then from A, then B would be much slower. But the same token, a processor can do its job better, which works on the data that's close to another data rather than farther away, allocating a large amount of space on. Okay, so it's about just tracking where exactly you have to make or access the data. So your seeker or whoever is trying to access that piece of memory, if the memory is contiguously allocated, so it will be faster operation. When your code calls a function, the value passed into the functions, that means the parameters, potentially pointed to data on the heap, and the function local value get pushed onto a stack. Okay, when the function is over, those value get pop off the stack. All right, so here it says that I don't think it's true for other programming language. If you have a pointer, I guess in Golang you are still accessing it onto the heap, but it says that when you are passing a parameter, uh, so the local variables get pushed onto the stack. When the function of those value get popped off the cell. Let me know if I'm correct. Right. So it says that whenever you are passing or passing parameters to a functions that may be potentially pointed to the data to the heap. Okay, so it means that your pointer is still on the stack, but data that is pointing to maybe on the heap. Keeping track of what part of code are using what data on the heap, minimizing the amount of duplicate data on the heap, and cleaning up unused data on the heap so you don't run out of the space are all problem that ownership address. So something related to garbage collector, but it seems that it's not exactly called a garbage collection here. It's called ownership. Once you understand ownership, you won't need to think about the stack and the heap very often. But knowing the main purpose of the ownership is to manage heap data can help explain why it works the way it is. Okay. So let's dive into what those rules are. We have been talking about ownership rules because these ownership rules are nothing but those that take care of all the memory allocations. So each value in Rust has a variable. Yeah, each value has a variable and it's called owner. Okay, so variables are owners. There can only be one owner at a time. Okay, so one value can be assignable to only one variable. That it's mean, I guess. When the owner gets out of the scope, the value will be dropped. All right. So this is, I guess, common. So whenever your value gets out of scope, your garbage collector kicks in and reclaims the memory. Variable scope. Now we are past basic Rust syntax. I won't include all the funk. Okay. As a first example of ownership, we'll look at the scope of some variable, right? So scope is nothing but it's a block where you can access the value of a variable. So for instance, in this, the scope of this variable is this particular curly braces. Outside this, you may not be able to access this variable because it's the scope. Yeah, as I mentioned, it's similar to other programming language. Okay, so it's taking an example of a string type to explain ownership. The types covered previously are all of known size. All right. So it means that the scalars are all of known size. Yeah, even arrays were of known size, right? So you have to define the size of those arrays, um, even tuples. So these are all can be stored on a stack, and when their scope is over, they can be trivially, they can be popped off once they're out of the scope. But we want to look at data that is stored on the heap and explore how Rust knows when to clean up that data, and the string type is critical. So we also get some sense there. If your data type is kind of fixed size, and we can kind of pump it onto a stack, else that goes on the heap, which can grow based on amount of data that particular values or variable is referencing. Also, so it says that we have covered string and modal in chapter 8. So it's interesting because strings are most commonly used data type in any programming language, and they are covered more in chapter 8. Right. So here, let's see. I'm not going to read this. We have allocated a string from I don't know what they call it, as a string literal or something. So let's read that. String literals are, but they aren't suitable for every situation. One reason is that they are immutable. Strings are immutable. I think that all the variables are immutable. I'm not sure why they're calling it as immutable, because everything is immutable. I'm not sure whether it was the point in again telling that the strings are immutable. Another is that not every string value can be known when we write our code. For example, what if we want to take user input and store it? Yeah. For this reason, Rust has a second string type called string. This type manages data allocated on the heap and as such is able to store an amount of text. Okay. So because our string most of the time are dynamic values, it's better to pump it on to the heap so that that can grow according to the memory available to the heap. So let's run this. It's simple. It will create a string from hello. Again, no output. Okay, we are not printing anything. Obviously, there won't be any output. What is this? Oh, can we? Okay. The double colon scope resolution operator, also us to namespace. Okay, so they are going to cover in chapter 5 about this double colon that you see here. This kind of string can be mutated. All right, so again, yeah. So you can just push underscore str. So I guess that's what we call associated function. I'm not sure whether this is an associated function or not. I guess associated functions were a part of crates. Uh, Let me check what exactly associated functions for Rust. Yeah. So methods are similar. I guess we will come to this later. Associate with don't take self. Not that great explanation. So if you know, probably let me know what exactly is an associated function. All right, so let's start to code, right? Let's go back onto project, create new ownership. Create not one. Oh, sorry, cargo. Oh, I'm going. All right. Open this. Let's try to do it from the memory. So I will create a mutable string, and that will be part of string. And it says that from. So that will be hello world. Yeah, I guess today IntelliSense seems to be better. I installed some plugins maybe because of that. I'm not sure whether. So it will say that it's not mutable. It says that variable does not need to be mutable. By default, it's what? Note one unused. Okay, because it's not mutated yet. So s dot push something push string. Oh, now this is working. So we are going to push that string. Oh, just a single string. Hello world. I'll use some space. Dot. Today is great. Yeah. Let's print this. Println. Ah, today things are working much better. Yes. I'm not sure why we can't just do this and get ahead. We always need a placeholder. I'm not sure why they designed this way. Anyways, semicolon. So if you're coming from Golang, right, you would probably miss these semicolons. I'm not sure why ID can't do that. Maybe ID just automatically add that semicolon when you are. So for that, I guess need to find some plugins if there are. So cargo run. I will first clean this. Anyways, cargo run. 'Cause I go 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 run. 'C cd ownership cargo run. Huh, looks good. I guess this should go like this. All right, so we have created a mutable string here. So I will take this out so that I do not have to create. So I will create a function mute string. As every time I have to create so many projects, right? Just goes here, and I just call this mute string from here. So you can just keep on commenting this and keep on calling for today's exercise. So what's the difference here? Why can string be mutated, but literals cannot? How these two deal? So let's see. In the case of a string literal, we know the contents are compile time. So the text is hard coded directly into the final executable. This is why string literal are fast and efficient, right? Because they are capped, they are hard coded, but only come from the string literal's immutability. Can't put a blob of memory into the binary for each piece of text whose size is unknown at compile time and whose size might change while running the program. All right, so that's the problem with the string because their values or their size can mutate over the time. With the string type, in order to support a mutable, growable piece of text, we need to allocate an amount of memory on a heap unknown at compile time to hold this content. This means the memory must be requested from the memory allocator at runtime. We need a way of returning this memory to the allocator when we are done with our string. All right. So whenever your memory requirements are increasing during runtime, so you are going to request certain amount of memory from the memory allocator, and then when you are out of scope or that string does not require anymore, you can just kick the garbage collector. Again, here there is no garbage collector. I assume there will be garbage collector. I'm not sure why they have still not mentioned it. They're calling it as ownership rules. Let's see. Okay, so first part, the allocation is done by us, or the request of the memory is done by us to the memory allocator. The second part is different. Language with a garbage collector keep track of clean up memory that isn't being used anymore, and we don't need to think about it. In most language without a GC server responsibility to identify when memory is no longer being used and call code to explicitly return it, just as we did to request. Doing this correctly has historically been a difficult programming problem, right? So some of the programming languages Java has stop the word scenario, right? Where for some seconds your program may freeze because it's going uh, major GCIS. Okay. Rust takes a different path. The memory is automatically returned once the variable that owns it get out of scope. All right. Automatically to return. I'm not sure how it's automatically for us. It means that as a coder, you do not have to, but obviously the memory allocator will reclaim that memory. I'm not sure on this one either. Maybe they are going to explain this in bit detail. Yeah, so we printed it. Maybe we do few more operations that do not access it. So I guess after that scope or after that function terminates, your memory is just reclaimed. When a variable goes out of scope, REST calls a special function for us. Okay, that's what I was talking about. Nothing is automatic. This function is called drop, and it's the author of string can put the code to return the memory. REST call drop automatically at the closing bracket. Okay. So I guess we can also create our custom data types, and these data types should implement this drop function because these drop function are called by Rust runtime, and it will automatically reclaim the memory after this variable goes out of the scope. All right, so ways variable and data interact. Multiple variables can interact with the same data in different ways in Rust. Let's look at an example using an integer in this one. Okay, that's simple. X points to y, y points to x, binds the value 5 to x, then make a copy of the value in x and bind it to y. Now we now have two variables x and y and both value 5. This is in, I guess this is a copy of the value here, not the reference. So even if you change x, I don't think your y should change on later. Yeah, obviously they're pushed into the stack, so they're not referencing the heap. Yeah, now this is a string, so this gets into the heap. Let's see. This looks very similar, so we might assume that the weight will be same. That is, the second line would make a copy of the value s1 and bind to s2, but isn't quite the happening. Right? Take a look. What is happening to a string under the cover? A string is made up of three parts. Can we copy this? So I'll copy this maybe once I'm finishing editing this. Why? Oh, this is needs a reload. It's not allowing. Anyways, so it says that a string consists of these three things. One is the pointer. Another one is not the string, but this one, this particular variable here, a length. So it's essentially not a simple variable, but a pointer. So it's these three values. This group of data stored on the stack on the right in the memory on the heap that was okay. So this particular S1 that's residing on the stack, but this particular value is residing on the heap. The length is how much memory in bytes the content of the string is currently using. The capacity total amount of bytes that the string has received from the allocator. The difference between length and the capacity matter, but not in this concept. So it's fine to ignore the capacity for now. Maybe later on in chapter number 8, we will be dealing with this. When we assign S1 to S2, yeah, same thing. So when we kind of say that S1 S2 is equal to S1, so this means that now S2 is pointing directly to the value that's stored in the heap. So anything we are changing here with S1 gets reflected, or using S1 in the heap get reflected into S2. So it's not a copy that we may assume with the primitive data type what we tried in step one, right? Yeah, if we have copied, then it will be very expensive because we would be allocating twice the size of this data in our memory. Earlier, we said that when a variable goes out of scope, Rust automatically calls the draw function and cleans up the heap memory for that variable, but shows that both data pointer pointing to the same location. This is a problem when S2 and S1 go out of the scope. They will both try to free the same memory. This is known as double free errors, right? So we were saying that uh, whenever a variable goes out of scope, there is a draw function that's get called by Rust runtime, and they are going to call it twice, right? So this may lead to memory corruption. So how do we ensure that memory safety? Rust consider S1 as no longer valid. All right, so now Rust only consider the S2 and S1 is doesn't need to. S1 goes out. Check out what happened. Okay. So I guess even if you let S3 is equal to S2 over here, then I guess it will be S3 that will be valid and the rest all the pointers pointing the same memory location, those will be invalid. Right? Ah, that's also interesting. I was not expecting this. I was expecting that it's just on the background that Rust will have some flag so that drop doesn't get called. So here S1 is no longer valid. That means that now we cannot even access the S1. That's strange. It will be interesting, like what will be the use case of this one, because those two pointers are pointing to the same values. Okay, so this term, the shallow copy and deep copy, so this was nothing but a shallow copy, but it seems that this also invalidates the first variable. Is known as a move. All right, so just a move. It's not a shallow copy anymore because your first variable is now invalid. Interesting. In addition, there is a design choice that's implied by this. Rust will never automatically create deep copies of your data. All right. Therefore, any automatic copying that can be assumed to be inexpensive in terms of runtime performance. All right. So I'm just copying all these statements that are important, and I'll be sharing it onto the Medium as well. I've already shared 001. Yesterday I couldn't, so probably I'll just um, merge today's and yesterday's notes and share it on Medium today. Okay, so we also have the capability of doing a deep copy. And here, so we have a function called clone. We can use that function, and now I guess this will create a different pointer. And now we have both an S1 and S2 available for us. Let's copy this and try to execute this. Fn deep copy for the strings. Deep copy. What is it? Okay. Says that it's not called, so I'll comment this out. All right, so both S1 and S2 are getting called, and I guess right now we have the copy of the data into the heap for S1 and S2 both. So that's explicitly deep copy. There's another wrinkle we haven't talked about. This code using integer part of which we shown worked valid. Still valid and done. The reason is that such type have known size at compile time are stored entirely on stack, so copies of the actual values are quick to make. That means that there is no reason we would want to prevent X from being valid after we created Y. Alright, so here it says that stack, these sites are constant based on the data type we have defined. So we can actually make copies so that those copies are real quick to make onto the stack. Yeah. So copy this one and put it here. So Rust has a special annotation called the copy trait that we can place on types that are stored on the stack like integers. We talk more about okay in chapter 10. So just for now, just remember that there is a copy trait that can be placed on the type. If we implement the copy trait, a variable is still valid after assignment to another variable. Rest won't let us annotate a type with copy if the type or any of its part has implemented the drop. So there is another trait called drop trait. If the type needs something special to happen, I guess I'll just skip past it. That's too much data to grasp right now. So just for now, just remember that there is some traits which are called copy and drop. I guess this we will discuss more in chapter 10. Yeah, I'll just skip past this copy trait. I guess it's right now too much to digest so much of data. Okay, so let's look at this example. The semantic for passing a value to a function are similar to those for assigning a value to a variable. All right, passing a variable to function will move or copy just as assignment does. So here, S. So this means that S value move on to the function, so no longer valid here. X comes into the scope, X would move into the function, but I32 is a copy, so it's okay to still use X afterwards. All right. So one thing that I want to look here is if I print S and this particular function takes ownership, changes the string, what happens, right? Let's try that. Maybe they have tried it later on, but we are more curious than them. Okay, function string ownership. So we'll just comment these for now. String ownership, that's it. And this takes the ownership, and I will also try to change this one. So I'm not sure whether this is immutable. This must be immutable by default. Everything is immutable. So sum string dot, what was add sign? No, push string. Push string, some value. What was hello Mohit? Yeah, I guess this is, but there's some error. Okay, so this is mutable. Can I? No. I don't care whether it's mutable or immutable, so I'll just add it as immutable here. Oh. Mm -mm. So let's carry some mutable str some string, and then I am going to push this here, and if I try to print it over here, yes. Oh, that's the problem in the Rust. I'm not sure why they have decided to print this. What it says. Hmm. So I guess we need to look into this copy thread that we just skipped past. So it says that when ownership has been changed, so we cannot print something. So this goes out of the scope, and we would not be able to access this here. So what this instead can be done is, I guess, something like this, and we can just return str here, and here we can have another str. Let's go to this. Oh, sorry, on line number 18, and this prints here. All right, so I guess that's kind of rule driven. Mm, so how? So now let's try to go through whatever we learned with this particular piece of example and how that makes sense in the memory management realm. So here we have defined a string that's again immutable, and we have passed it over. Now I guess this gets invalid once we have passed this s to this one. So what is valid now is some string, right? So once we are passing it around to another str, now this particular some string. So let's try to do that. Try to print this here, and I'm sure here this won't allow us to access the some string because that's now invalid as the rules mention. Yeah. So let's see that where the some string. Yeah. So this will be invalid because that's now assigned to this. And so, okay, this makes sense now why this ownership works the way it works. Primarily for the string because that prevents us to to have multiple copies of the same data. Apart from that, if we would have passed this particular primitive and we would have printed it, definitely we will be able to access this because we have passed on the copy of the primitive instead of passing on the on the pointer to the value stored in the heap. So if we do a println here, so this will definitely work. Should work. Oh, okay. That's crazy. Yeah. All right. So let's print this as well. So hello. So hello is this one. Hello Mohit is this one, I guess. Are we calling anything else? Takes ownership. Are we printing anything? Okay, this one is hello, and then we are push str, push string. I guess similar to append. All right, so this makes sense. So I don't think I'm going to read about the copy here. So things are clear. Yeah, I guess same thing they're trying to do it here. So I'm just skipping past this. Return, we already saw how to return the values. Oh, we do not even have to just do the return as we mentioned that the last expression is itself a return. So I can just do this and remove this, and this is my return. Yeah, no semicolon because then it's not an expression. All right. Before going to 4.2, I'll just take a short break and then we will be back to continue on borrowing, right? So new to this one, I'm not sure how do I. Okay, I can just audio capture. Oh, so that's interesting. All right, just let's get started to the point where we left. So ownership, I guess it's kind of clear now. So in brief, if your data type is dynamic, so essentially there is a shallow copy, and the first variable uh, that was copied from, it's invalidated. And this doesn't hold true for the data types which have constant memory space requirement. All right, so there is also 4.2, and here it talks about references and borrowing. Let's see what it is. The issue with the tuple code and for that we have to return a string to the calling function. So so that's what we did, exactly what we did. So we have to return. Hmm. Okay, so there we were passing it as a value. Here we are passing as a S1. So I guess if you're passing as in S1, then that, okay, we have not created another one. So it's just point to that, and we have still S1 validated. We do not have a new variable for this particular string. All right, so this makes sense. Okay, same thing. First, notice that all the tuple code in the variable declaration and the function return value is gone. Second, note that we pass add ampersand s1 into the calculate length, and in its definition, we take ampersand string rather than string. The ampersands reference references without taking ownership of it. Okay, so it just points to that specific location in the heap without taking the ownership. So once we are assigning a variable, I guess that's the ownership. Yeah, so the same ampersand we can also dereference it by pointer. So that means the value that this referencing operator is pointing to. Let's take a closer look at the function call here. S1 is this one. Length will be calculate length. The ampersand S1 syntax lets us create a reference that refers to the point of S1, to the value of S1, but does not own it. All right. So I'll just copy this line for our notes. So ampersand, it just creates a reference, but does not has the ownership. Because does not own it, the value it points to will not be dropped when the reference stops being used. Likewise, the signature of the function s ampersand s to indicate that the type of. All right, so this is slightly different from other programming language. So this will be a pointer, but here there is slight distinction between a pointer and reference. So in Go, you would probably do an asterisk string. Here it's again an ampersand string. The scope in which the variable s is valid is the same as any function parameter scope, but the value pointed to by reference is not dropped when s stops being used because s does not have the ownership. All right. So reference, even if this goes out of the reference, the value pointed by s is not dropped because it's just a reference, doesn't own anything. That's what it's saying. We call the action of creating a reference borrowing. Okay. Creating a reference is nothing but a borrowing. As in real life, if person owns something, you can borrow it from them. When you're done, you have to give it back. You don't own it. Yeah, if you have the friends, then even if they're borrowing it, they won't return it. So that's slightly different. Are we doing on correctly on the Twitch? It seems so. Let me know in the comments if you are facing any issues with the stream. Okay, we'll continue. So if we modify something, I don't think this will allow it because borrowing, so you won't be able to change it. I guess that's mutable. Attempting to modify a borrowed value. Okay, so we cannot modify a borrowed variable. Mutable references. Modify a borrowed value. Yeah, but for that, I guess your string should also be mutable. If that's mutable, then you will be able to borrow the value. Give me a second, guys. I will be back. So here we can also create a variable references, but I'm not sure whether just searching something. Let's see that. Okay. So you can have only one mutable reference to any of these values. I'm more interested in this one. Let's start with this. And let's also try to see that the value changes or not. So this gets mute reference. So just call it here. Mute reference. And just puts it there and I'm going to enter this. Alright, so this reference will mutate this particular string as well, if that's mutable. So it's, my initial statement was slightly wrong. The reference can mutate the values they through the pointing to, but they do not have the ownership. This is still point ownership is with business. And then if we try to have these mutated strings, then we will be able to say mutate the values pointed to this bias. So there is also one rule. You can create only one mutable reference to point it to this. Right? So if you have more than one reference to a mutable data and you try to mutate it, so the important thing is mutable reference, not a sample reference. You can have immutable and as many as possible, but only have one mutable reference because that rule requires that. Normally, this restriction tags here data is to a pointer to a more pointer access the same data at the same time. At least one of the pointer will just write the data here. So if you have multiple mutable references, so they will try to change the data state, and that can cause an issue. So I'm just skipping past this. So much of information right now to digest, I can understand that, but we learn like so much of the memory model, I guess, for us, and now it's using the concept of the scope to have some control or the ownership rules, so that we do not have the memory issues. Okay, I'm just skipping past this and I'm learning directly to the dangling references. Yeah, we have the dynamic pointer, right? So we have created a pointer, but later dynamic points to nothing. The pointer that reference a location in memory, that may have been given to someone else by freeing some memory while preserving a pointer to that. C, C++, this dynamic pointers, so that memory may point to something else. In Rust, microcontroller the compiler directories that the reference can never be a dangling reference. If you have a reference to some data, the compiler will show that the data will not go to scope before the reference to the data does. So Rust will not have this dangling reference. So what does that mean? So dangle returns a string. It returns a reference to that string. Now this is useless lifetime, so we will be discussing lifetime later. Returns value contains a borrowed value, but there is a rule that is for it to be borrowed from. You have a reference to this one, but then after that, there won't be anything be done to this, so it's kind of useless to create a reference. Let's read through this. Because S is created inside Django, when the code Django is finished, S will be deallocated, right? Okay. But we try to return a reference here, that means this reference will be pointing to an invalid string. That's not going to respond to this string. So this goes out of the scope, this points to nothing, but still we have a reference that we have tried to transfer it to this value, but now that's dropped. So still valid, so memory goes away. Yeah. So this then let's return a string. Now you're holding to add S, so we are storing this. And so here, if you return this S, now this will go out of the scope. I mean, this will be invalidated, and this still will be holding the value for this one. Right, simply. So the rule of references, you can have either one immutable references or n number of immutable references, and references must be correct. So last point, the dangling reference was also this one. So you should not be a dangling reference, so even if you need access, because this doesn't make any sense after this goes out, cannot make any changes using this borrowed memory reference. All right, so lot of things to digest here. Let me quickly go up and go through this once more. So there we talked about the reference, the right, because reference doesn't own anything. So we can still, so this still stays in the scope here, and here this by default is mutable, so if we try to change this one, and this will throw in an error. So what we have to do is create a mutable S1, again reference will also be mutable, bug you with that amount of information that you're already exhausted. So let's go to slice type real quick. Oh my goodness. Okay. Slice lets you reference a contiguous sequence of elements and connections rather than the whole connection. Okay, so it's kind of slice is a piece of an array, maybe a piece of a tuple. I'm not sure it's the tuple for this one. That takes a string and returns a float. That can be a slice of a string. So you can have a substring and a string. That takes in a string and returns the first word it finds in that string. That means you have to find a space in that string so that is the first word. So let's see that what they're doing. So that's a byte, I guess. Bytes, I guess that will be a byte array, I'm not sure. So you can have s.as underscore match. It seems that Rust as is snake case colon camel case brought as snake case as requirements related with snake case. So for I, the enumerate if item equals to p, what is the p followed by this one? I guess that's for space. I guess I'm not sure. So it provides an iterative. Let's first go to this. You need to go to the string element by element and check whether value space will convert the string to an array of bytes using hash space. So it's an array of bytes. That's why you write it and you get my following. So similar to this one. Now we create an iterator over by using the iter method. Here this iteration located several method. There is a method that returns each element in the collection and that enumerate wraps the result of item and it returns each element as part of a tuple itself. The first element tuple returned is the index. Okay, that's what we were trying first, right? Now can we try that? I'm not sure whether that's. So that's for loop. Yeah. For I guess like this. Does it return a tuple? Okay, so does it return a tuple? And iterator over there. So this return a tuple first and the next second one is the value. Inside the for, we search for the byte that returns space. Byte returns syntax. Byte, we find space, we return the position. Otherwise, we return the length of the string by using s.length. Okay, so this one, we do not find a space, so probably we have only one string or one word. I'm not sure what does that mean really. Let's read through this. We now have a way to find out the index of the end of the first word in the string, but there is a problem. We are returning a useID option, but it's only meaningful number in context of random other because it's separate value from the string. There's no guarantee that it will still be valid if you configure the program and refine that way to the first word. Or it will get the value file. And it seems to me right now that's a lot of information to digest for now. But let's read through this again. Kind of. We now have a way to find out the index of the end of the world in the first string. But there's a problem. We are returning a new site on its own. What's the size? We are returning a new site. After calling a stop here, was word isn't correct. Okay, so it says that even if we clear this, word is still pointing to 5 because that's the value we have received. Yeah, that's fine. Here would use the value 5 with the variables to try to extract the first one, but this will be impossible because of the content of a section instead of here. You say 524. Depends. You know, because we have cleared, we haven't cleared the word, so already we have this understanding. But okay, having to words, so what they're trying to say is they want to have a value that's dynamic with this x. So this exchange, so again, I guess we will be using a reference to it. So it says that this particular word should be connected to S. So if this gets cleared, the word should also change. Still it contains the value 5. We would be having 5 to try to convert this to okay. Having to worry about the index and word getting out of sync with the data is tedious and overthrown. So let's see that how they're trying to solve that. Tracking starting and ending index. And we have even more values that were calculated from. We have 3 unrelated variables floating around and they need to be kept at the same. Okay. So what it says that so for this problem to be solved where the length is kind of, or the word is kind of connected with the outer world middle line. So we have something called string slices. So it has period string, and it is 0 to 5 word, I guess, word. And the second word will be word. L is a reference to the pointer of the string. We create slice using a range within a bracket by specifying starting index and ending index. The first portion of the slide and then everyone more than the last position in the slides. The terminal slide with descriptor shows the starting position and the length of the slice. Alright, it corrects. So starting position is 0 and length so it's just an offset so that you can have starting position and offset to get the complete substring. Case of let's word with a slice that contains a pointer to the byte and then a 6 of s with a length values of 5 for it. With Rust, with Rust, range syntax, if you want to start it like 0, you can draw the value before the repeat is. Okay, and if you drop it, so it will be heading to the length. Then drop both. This complete string is common to almost all the programming languages. Okay, so they are using now the slice concept that we learned uh, to to rewrite this first word. So what they have done, alright, so they have returned a reference that points to 0 to I. So without a straightforward API, that's much hard to mess up because the compiler will ensure the reference into the string remains valid. Remember, the bug in the program when we called an index to the enable word, but then clear the string so an index word and learn. The code was logically correct, but didn't show any metadata. The problem was string operator and we kept trying to use the first story device with an empty the slice made this bug impossible. So this kind of throw that error. Yeah, because that's slide, that's a reference cannot borrow less than mutable because it's also bound to be mutable form because because in borrowing that if you have an immutable reference to something, you cannot also make a mutable reference because there is to something the string. It needs to get a mutable reference. The print element after the call to play with the reference. So the immutable reference must still be active at that point. Alright. This allows yeah, the same what we discussed last time. The immutability discourages any changes made to this one. So this kind of safeguard and anything is being done because the reference is immutable. String literals are slices. These are slices. Alright. The type of STR is ampersand STR. It's a slice pointing to a specific point of the binary. This is why string liter is immutable. Alright, so these are immutable because these are immutable over references to a string. Knowing that you can take slice of literals and string value in the fluent component out of the first word and signature. More extreme illustration would write the signature shown is instead because it allows us to use the same function on both string value and str values. Yeah, because that's this one. Oh, we just missed this str. Right, that's for the slices. Right. If you have a string slice, you can pass it directly. If you have a string, you can pass a slice on the string or a reference to the string. This flexibility takes advantage of DF coercion. Okay, that's part of chapter 15. Define a function to take a string slice. Instead of a reference to string, we cover it in more general and useful without losing functionality. Other slices you can also have slice to an array. Yeah, we already saw that. I did these are indices, so this will be from true to put it to the last 0, 1, 2, 3, x 2, x 3. Yeah. Okay, so again, slices are nothing. You store the values. So there's the two values. One is the reference to the first element, and the other that's the offset. All right, guys. I guess today it was too much of the theoretical part, too much into the concepts of slice and but I guess we right now are into the rest territory, the concepts or the core concepts that make up the Rust, because some of the concepts are like common to almost all the programming language. These programming language differentiate because of the specific nuances of specific programming language. Like in Rust, we have the concept of ownership, references, immutability of references, borrowing, Hmm. Not much of the coding today. I thought that we would be trying those three questions, but I guess right now it's too much of the information for us to digest for today. So I guess what we will do is end our stream at this point. Maybe we will try to do some exercises in the evening if I'm online, else we will do it today, tomorrow. Meanwhile, try to go past this chapter 4, what it seems to be. I guess ownership rules and reference and borrowing quite clear as I would expect, but how to use these theoretical concepts into our programming exercise, that will be key how we develop the intuitiveness and all these concepts, specifically fries. Because right now, I guess have read this through this, kind of understood this, but to translate this theoretical knowledge to the practical knowledge, I will that will come out of experience and practice. But for